All right, so good afternoon, everybody, and thank you for coming today to attend my presentation on the atomic deposition of tin oxide on carbon nanotube membrane for photo and electro-catalytic applications. So actually, my name is Ahmed Rashed. I'm a third-year PhD student at Deakin University, and this project is part of a collaboration between Deakin University in Australia and Lentec of America in USA. Lentec provides me with the carbon nanotubes that I'm using in my research, and also I have a chance to do some work at the Melbourne Center of Nanofabrication and using some of the facilities there, which is a big advantage for my project. So to give you an idea about the project, I will start with a context about the project leading to the research question and the research plan. As you may know, human health has been seriously endangered by the presence of persistent organic pollutants, including pharmaceutical waste. And this pharmaceutical waste is very dangerous because most of pharmaceuticals are non-biodegradable, and also they are very chemically stable in the environmental media, which can be very detrimental to the biosphere and the ecosystem. So over the years, various methods have been used to remove these pharmaceutical pollutants, including the physical methods and the chemical methods and biological methods. However, each of these must have some limitation. For instance, biological is not suitable because pharmaceuticals are non-biodegradable, while the physical method can suffer from membrane fouling over the time. Therefore, research has been directed toward advanced oxidation processes using generation of oxidizing species to oxidize the pharmaceutical pollutants. And here it comes the role of our carbon nanotube material, because it has a very interesting properties, high aspect ratio and high absorption capacity, so it can promote the catalytic activity. Although CNT itself, the pristine CNT doesn't have any catalytic properties, but and also we have some challenge in the fabrication of the carbon nanotube membrane itself because of the requirement for the functionalization of carbon nanotubes for the processing of this material into a robust membrane structure. But I will show you later how we overcome this problem. So what else we need? We need to add a catalyst layer on top of the CNT membrane surface, and we have selected the atomic deposition technique because it's a very precise technique that can produce a very thin layer of catalyst metal oxide layer on top of CNT surface. It's actually a vapor-based deposition technique based on the pulsing of chemical precursors separated by purging of inert gas. So we can, by optimizing the dosing time and the purge time, we can have a consistent growth per cycle, and we can also have a control, select the deposition temperature suitable for the deposition of the target material. And here we selected the tin oxide specifically because it can be deposited at relatively low temperature, around 100 to 150 degree, and also it has a interesting, excellent photo electrocatalytic properties. So now, what is the plan, and what is the research question? The question here is how can we use this dropper carbon nanotube and tailor them from the nanoscale to the macro scale to end up with a catalytic membrane reactor that can achieve cost-effective remediation of pharmaceuticals. And the plan include CNT membrane fabrication followed by surface modification and then evaluation of the performance. All right. So the CNT membrane fabrication, as I mentioned, we have a challenge in the processing of the carbon nanotube material, but in this simple method, we can achieve the fabrication without the need of using any harsh chemical or any functional addition. We just have a CNT forest from Lentec, And we spin these vertically aligned carbon nanotubes to horizontally align them on polymeric ultrafiltration membrane. And then we densify the CNT webs by ethanol spraying, followed by the drying. And then we have a robust, as you can see, robust CNT membrane. So interestingly, we have different parameters that we can control to optimize the thickness of this layer of CNT membrane, and also the orientation, so that we can control the pore size, the electrical conductivity, and so on, as you can see here in the SAM images. And then we apply the atomic deposition technique on top of the CNT membrane surface, and as you can see here at the lower number of ALD cycle, the tin oxide start to nucleate around the CNT walls. And then by increasing the number of ALD cycles, we can notice an increase in the diameter of carbon nanotube due to the deposition of tin oxide. And when we measure the spacing of the lattice fringes, we can see it's corresponding to the tetragonal tin oxide structure. And this was also confirmed by the EDX mapping and the elemental analysis, as you can see. And then we characterize these nanocomposite membranes, and you can see here that we have different properties. Interestingly, the membrane surface roughness and wettability were improved, and also the band gap was reduced so that it can be used in the visible light photocatalysis as well. And here's the photo electro-catalytic setup that I have used in my research. And we use the methylene blue as organic model pollutant. And then here is the results of the membrane, the performance testing. K here represents the rate constant of the reaction. And you can see here with increasing the number of tin oxide, the thickness of tin oxide, the rate slightly increased, and then it decreased due to deterioration of electrical conductivity with higher thickness of tin oxide. And then the photocatalytic activity was consistently increased upon deposition of tin oxide up to 25 nanometer, and then it started to plateau or decline due to the limited light penetration at higher thickness of tin oxide. So you may wonder how these membranes are working. So I will give you just brief explanation of the mechanism. The photocatalytic degradation mechanism based on when we irradiate light, UV or visible light, the electrons are excited from the valence band of the tin oxide to the conduction band. And then oxidizing species are produced, superoxide and hydroxyl groups that can oxidize the organic pollutant. However, we have a problem that these electrons can recombine by the time, but we have the carbon nanotubes that act as an electron sink to trap these electrons. And this is the advantage of carbon nanotube. And for electrocatalytic setup, we oxidize the CNTs by anodic oxidation directly or by hydroxyl groups indirectly. So in conclusion, the spinning of drawable carbon nanotube can be a very promising technique for fabrication of CNT membranes with controlled morphology and properties. And atomic deposition can be used to add a catalyst layer with a precise thickness on top of the CNTs. And this work actually offers an effective way to have a scaled up scheme for the fabrication of carbon nanotube catalytic membrane reactor for cost and fast remediation of water effluents. And the future work include testing this membrane against synthetic pharmaceutical pollutants. So last but not the least, I would like to thank all the team at Deakin, contributors and collaborators in USA. I would like also to thank all the staff members at the Melbourne Center of Nanofabrication for their extensive support. And also I would like to thank my supervisors, all my supervisors at Deakin, in Emirates and in USA. And finally, thank you all for attending my presentation, and I'm happy to have your question. Thank you.
Thank you very much, Ahmed, excellent talk, and thanks for sticking to time. Now I'm just checking the slide, and I can't see any questions there. Is there any question from the audience here? If not, I might make a start. So you're formulating this as a membrane. Is the idea that ultimately you want to flow the solution through it? Because what you showed is actually just a electrode setup without any flow through the membrane. So. Yeah,
I'm so happy with this question. Yeah, because it means that you really focus on the target of the work. We do want to have a catalytic degradation, also separation through the flow of the water effluent. And actually, we have designed the membrane reactor to test the membrane for the synergistic separation and degradation. And this will include also the flow of the solution across the membrane. And then you can imagine if you have this degradation rate along with the separation after the filtration process, we will have much more improved performance. But since the reactor is still under design, I didn't include the results of this reactor yet. Yeah.
Okay. Just one more quick question. With the ALD, do you have any appreciation whether the deposition, the layer thickness is the same across the 30 layers of the, so that the thickness of the metal oxide layer across the 30 layers of the carbon nanotube?
Yeah, exactly, because I was very happy with how the ALD system at MCN is very, very precise and controlled thickness. You can see here in this image that I measured the thickness of tin oxide on a silicon wafer. It was around, after 250 cycles, it was around 25 nanometer. And when I measure the thickness here, it was also around 25 nanometer, matching the measurement that I have done using the ellipsometric technique at MCN, which means that yeah, we can with using this technique, we can have a precise control over the thickness.
Fantastic.
Yeah.
Ahmed, thank you so much once again for kicking us off, and please join me in thanking him.
Thank you.